Suppose the greatest common divisor of a and p is 1, and a to the power p minus 1 is congruent to 1 mod p. This will always happen if p is prime, but could it happen for non-primes? If it does, we say that p is a pseudoprime to base a. We might expect pseudoprimes to be rare, so concrete doesn't hurt. Let's try to find pseudoprimes to base 2. So a useful strategy is to collect all the properties. And remember, it's the journey, not the destination. Suppose n is composite, and 2 to the power n minus 1 is congruent to 1 mod n. Since n has to divide 2 to the n minus 1 minus 1, then 2 to the n minus 1 minus 1 is composite. So what do the factors of this number look like? So remember, math ever generalizes, so to make it a little easier to write our notation, let k be this exponent n minus 1, and let's go ahead and make our base x. So let's consider the factors of x to the k minus 1. So remember, we have the root theorem. If f is a polynomial and f of a is 0, then x minus a is a factor of f of x. And since x equal to 1 makes x to the k minus 1 equal to 0, then x minus 1 is a factor, regardless of the value of x. So for example, we might try to find a factor of 6 to the 20th minus 1. We note that 6 to the 20th minus 1 is just x to the 20th minus 1 for x equals 6. And since x minus 1 is always a factor of x to the 20th minus 1, then 6 minus 1, 5, is a factor of 6 to the 20th minus 1. Now remember, 2 is an odd number. While this works generally, it will fail with numbers of the form 2 to the k minus 1. In particular, something like 2 to the 20th minus 1 will have a factor of 2 minus 1, but that's just 1. So what else can we try? So remember, sometimes it's helpful to just sweep things under the rug. Note that we can substitute and rewrite x to the 20th minus 1. For example, if we let y equals x squared, then x to the 20th minus 1 becomes y to the 10th minus 1, and by the same argument as before, y minus 1 is a factor, and since y equals x squared minus 1 is a factor. So let's try to find 3 distinct prime factors of 2 to the 20th minus 1. So our expression is x to the 20th minus 1 evaluated at x equals 2. So if we let y equals x squared, we can rewrite this as, and y minus 1 is a factor, and since y equals x squared, that means x squared minus 1 is a factor. So one factor will be 2 squared minus 1, 3, which is prime. If we let z equal x to the 4th, then we get, and z minus 1 is a factor, and so x to the 4th minus 1 is a factor. And so a second factor will be 2 to the 4th minus 1, which is 15, and we already know 3 is a factor, and 15 is 3 times 5. This means 5 is a second prime factor. And if we let w equal x to the 5th, we get, and so a third factor will be 2 to the 5th minus 1. So what if we have an odd prime other than 2? If n is even and greater than 2, it obviously won't be prime, so let's focus on the cases where n is odd, and so n minus 1 is even. In general, 2 to the power n minus 1 will have a factor of 2 to the k minus 1, where k is a factor of n minus 1. And since n minus 1 will be even, k is necessarily greater than or equal to 2, and we can always find a factor. Now if n is a pseudoprime, then 2 to the n minus 1 will have a factor of n. But if k is a divisor of n minus 1, 2 to the n minus 1 will have a factor of 2 to the k minus 1. So we want to have a factor of n We know we have a factor of 2 to the k minus 1, so what if we made n equal to 2 to the k minus 1? So remember, you can assume anything you want as long as it's explicit, and concrete never hurts. For example, if k equals 3, then n is 2 to the third minus 1, that's 7, and 2 to the power n minus 1 is, and so 7 divides 63, and 2 to the power 7 minus 1 is congruent to 1 mod 7. Of course, 7 is actually prime, so this shouldn't surprise us. To get a pseudoprime, we need n to be composite. Now, since n equals 2 to the k minus 1, it will have a factor of 2 to the power k prime minus 1, where k prime divides k. So let's consider composite values of k. Let k equal 6, then n is, and 2 to the n minus 1 is, which will have a factor of 63, except it doesn't. What happened? Well, remember, we wanted 2 to the k minus 1 to be a factor of 2 to the n minus 1, but this requires k to divide n minus 1. If k was 3, this gave us n equals 7, and 3 is actually a factor of 7 minus 1. But if k is 6, this gives us n equals 63, and 6 is not a factor of 63 minus 1. Put together, this means that if n equals 2 to the k minus 1 is a pseudoprime to base 2, k has to divide n minus 1. While this tells us the properties of a pseudoprime of a particular type, we still don't know if any exist. Can we construct a pseudoprime? Let's take a look at that next.